Thanks for coming. I'm David Disseldorp. This is Samuel Cabrero from SUSE, and we're going to speak about the witness protocol and its implementation in Samba. So we'll start off just with an introduction to Samba, and so we don't have a PA within the room, so I'll just have to try and reach everyone. I'll start off with an introduction to Samba and CTDB, or clustered Samba. We'll then move on to the witness protocol, some of the details of the protocol itself. We have a demo, so just a video of the witness protocol in action, and then we'll finish with sort of an outlook where we're heading with this stuff, what we need to do to get it sort of in shape for upstream. So starting off with Samba, hopefully you're all familiar. It's a SMB file server. It handles authentication, Active Directory integration, so you can join a domain controller or act as a domain controller. With Samba, we have one main daemon, one main file server daemon, which is SMBD. It's then generally forked for each client connection. We have a pluggable file system backend, so a VFS layer. And this is then what we use for things like Ceph. We have a libceffs integration. For Btrfs, we have some sort of snapshot-specific stuff. We have Winbind for the authentication, ID mapping, or AD integration part. With the protocol itself, we have a bunch of state, which obviously then needs to be tracked by the server. So for things like open files, leases, user mapping, we store that in a database. So we use TDB, or trivial database, for that on a standalone system. What was initially trivial is now sort of, I guess, had a bit of feature creep in that it supports things like transactions, record locking. We have multiple writers, so multiple SMBD processes writing at the same time to those databases. For clustered Samba, we then have CTDB. So this then handles, basically in the case of an active Samba cluster, we have these or a consistent database across all of these nodes. It also has a number of HA features integrated. So we have things like IP failover, service monitoring. It's I guess you could say a proper HA stack as well for a clustered Samba setup. Placement within the CTDB database is then computed based on a hash of the key, so we can find out from that the master, or a node which knows the location of that record, and from that location master we then have another level of indirection to find out where it's actually placed, so you can move records around the cluster to where they're needed. We have, amongst the CTDB nodes, we have election of a recovery master, and that recovery master then performs, in the event of an outage, things like cleaning up mid-transaction. That also holds a clustered mutex, or requires a cluster mutex. So with CTDB, that's generally placed on the clustered file system, backing the Samba servers or the file servers. With Ceph, we have sort of a helper binary which uses a Rados or Rados locks for that. For IP failover, it uses what's called a tickle ACK, which sort of speeds up the process of a client in the event of an outage, reconnecting to another node after IP failover. So this is then a look at sort of how things have changed or are changing with clustered SMB serving. So with Windows, in the past they've had active-passive setups where they have this file server role which moves across nodes within the cluster. Yeah, CTDB has always been active-active to the point that, or where clusters are then sort of spread across those CTDB or SMB gateway nodes. So now on to witness, Samuel.
Thanks, David. So, starting with the definition, witness is a new DC RPC.
Louder, please.
So, starting with the definition, witness is a new DC RPC based mechanism to inform the clients about changes in the topology or the state of the cluster, and it helps, together with new features in the SMB3 protocol, to provide transparent failover for the cluster clients. And additionally, it also can be used to load balance the cluster, because you can tell a client on demand to move to another cluster node. So before explaining how witness works, let's have a look at how failover was working in SMB1 and SMB2 clusters. So in a Windows cluster, we have a server that is holding the file server role. So the client opens the SMB connection to this node, and if the node goes down, the cluster moves the role to another server, but the client has to wait for the TCP timeout to reconnect. So after the TCP timeout, the client reconnects. So the protocol does not define any failover mechanism at all in SMB1 and SMB2. In a Samba cluster, I think the failover works better, because Samba implements additional measures to speed up the recovery, as David said before. The IP takeover, the gratuitous IRP, and TCL AC keys. So in a CTDB cluster, the IP, all nodes are active at the same time, and the IP addresses are distributed between the nodes. So the client opens the SMB connection, and when a node goes down, the cluster enters in recovery state and runs the IP takeover algorithm, which moves the IP address to another node. And after that, CTDB sends a gratuitous IRP to the client to inform about the new MAC address associated to the IP, and also sends a TCL AC key, that is a crafted TCP packet with a wrong sequence number, which has the effect of the client automatically reset the connection without having to wait for the timeout. So the client reconnect. In SMB3, Microsoft added new features to the protocol to provide transparent client failover. One is the witness services, that we are going to see how it works now, and another one is persistent handles. The idea, I'm just going to give the idea of persistent handles. And when the client opens a file in a server, the server has to store what is called the file handle state, which contains information about the leases, the share modes, and the logs. So if the server crashes, before persistent handle, this information was lost, but with persistent handles, this file handle state is somehow persisted. So the client can, when he reconnects, he can request the server to open, to reuse the file handle state. And in cluster environments, this file handle state is also synchronized or distributed across the cluster. So a client can open a file in another node in the same state. So in an SMB3 cluster, all nodes are running the witness service, and the client opens two different connections. And it's important to remark that these connections are always to different nodes. So when the node holding the file server role crashes, two things happen. the cluster moves the role to another server, and also the witness service tells the client about this movement. So the client can react and automatically reconnect to the other node. And now we are going to explain about the demo environment that we are using.
Can I ask a
Sure.
question? Okay,
Yes.
so you had those two servers, right? And I'm assuming that we are detecting the crash either with the client or with the second server.
So the question was, how is the crash detected for failover? And in the case of witness, it's generally driven by the cluster. So the cluster notices an outage and then tells the client about that.
So there is an independent entity that is detecting this, or it's the demons themselves?
So, it depends on the implementation. For Samba, we have CTDB basically managing the clustered SMB gateways. And in that case, they notice an outage of a node. So they're continuously monitoring the gateway nodes. They notice this outage and then notify the client for failover.
So I'm assuming if CTDB goes down, everything goes down?
If the quorum, or if the majority of CTDB nodes go down, then
So
yes.
there's a quorum.
Yes. Yeah. So just sort of explaining the demo setup we have. So we have our Ceph cluster. We have the Samba gateways. So in this case, 2 gateways in front of the Ceph cluster. These gateways are using the VFS Ceph backend for Samba. Also CTDB, then is the cluster service and key value store for Samba. Yeah, we have a bunch of changes on top of current mainline. So Samuel implemented the witness server. I worked on the async DCRPC server. Persistent handles were implemented by Ralph Boomer from Cernet. Yeah, we also have from Stefan Metzmacher, also from Cernet, the T-event impersonation changes. So it's a little difficult to see. We do get a pretty graph on the right-hand side, so we can at least see something later on. I'll try to sort of guide through what's going on anyway. So we have, these are the two CTDB nodes, and the corresponding witness server logs are, the other 2 black squares there. It's barely readable. So in this case, we're just initially connecting to the cluster. So this is a Windows Server 2012 R2 client. So here we can see, so we've just done a connection to the cluster. And here we can see that the client has then basically registered with the witness service. So it sends this async notify request to witness. And what happens now is that that request basically sleeps on the witness server side, and a response is sent when a notification is then ready for the client. So we're at least trying to show I think this is the SMB status output.
This is the output of, there is a new SMB witness list command that it tells you well, you will have to believe me. Yeah, it says that the client is registered on the CTDB node 1. This here is the client name. It's just the computer name. Here it tells you that the SMB connection is open to node class CTDB node 0, and this is the network name. Okay. So this is node 1. And this is the SMB status output. Just to check that the client is connected to one IP that is assigned to the node 0. This is the output, the association of the IP addresses to the CTDB nodes, and this was 13, and 13 is in node 0. So now we are preparing the SMB witness. The new SMB witness move command to tell the client to move to the other node. So SMB witness move the client name and the node, the new node. So
I guess we should say at this point, so in this case we're not triggering a failover. We also have, or at least Samuel implemented the ability to just do a manual notification, so to request that the client then move its SMB or file server connection from one node to another.
So the connection is throttle, is in KVM. So now when here is the output of SMB status to check the address where the client is connected. This is the node 1. So now we have to tell the client to move the connection, so it goes down, but the copy continues.
All of this requires client.
It requires the witness service on the client to accept these notifications or to notice these changes or act on these changes.
Now we are checking that the connection has been moved to the other node with SMB status and the association of the IP addresses in the cluster.
But what you're showing can also be done with durable file handles. I see no difference. So what's additional?
What is additional is, well, this could be achieved with Samba gratuitous IRP anti-kill easy keys. This is something new defined in the SMB3 protocol. That, I mean, gratuitous IRP anti-kill easy keys is a Samba addition, but it's outside of the protocol. Microsoft now has defined persistent handles and the witness services just for that. I mean, the kill easy keys was like a trick.
So I think the main point here is that there's no interruption to the application layer. So we have failover between nodes within the cluster without the application, in this case just an Explorer copy, noticing.
Yeah, but you can achieve that with durable file handles. I mean, just the same example you're doing with, if you do a CTV move IP and you have to implement a durable file handle, it will work just the same.
So in that case, basically there's an outage at the SMB protocol layer, and the client then forces a reconnect. In this case, we have a separate witness service, which basically tells the client, please move to a different node. So it's controlled and done at a layer separate to, or such that the application doesn't really notice the outage or the move between servers. So it was just a question on basically whether this could already be achieved with durable file handles.
And now here we have moved again the connection to CTDB node 1, and the file transfer continues. So.
He was just saying that he's moved it again from one node to another and then moved back again. Yeah, just while the copy is in progress. So, yeah, so that's sort of what we have as a prototype. Yeah, we still have quite a bit of work to do for upstreaming, mostly in the DCE RPC server layer. So we have this source 3 implementation of asynchronous DC RPC server. So Samuel has also worked on then merging the source 3 and source 4 implementations. So that gets us to, I think, a much cleaner point where we can then start upstreaming the witness stuff on top of that. Yeah, another possible future feature would then be automatic load balancing. So basically from the cluster side, seeing which nodes have free resources and moving client nodes, balancing client nodes between the cluster more evenly. Yeah, this is more on the Ceph side. So currently we have CTDB acting as then the clustered key value store. With Ceph backing the file server, we have another option as a key value store. So we can potentially look at using Ceph instead of CTDB, and then also making use of Rados classes to sort of offload some of the compute to the database.
Compute the database, can you expand?
So Samba does, so the question was compute of the database, can I expand on that? So Samba does some things like traversal to look up specific records. This is like incredibly intensive on, at least for a CTDB case. It's very inefficient. So using Rados classes for something like that, where we can offload that operation to where the storage or where the key value store is located would be.
Key value store would be basically offloaded to Rados itself, and then just call the...
No, so I think we'd still use the OMAP layer for the most part, or at least we'd start with just basic OMAP on the Samba side, and then when we see what sort of can be nicely offloaded to the cluster, we could then go down that path. I mean, just yeah, otherwise that's it. So I think we have a few minutes for questions. Otherwise, just grab us in the 2 minutes. So just grab us in the hall. Otherwise,
Any very pressing questions?
yes.
Isn't there a race condition on the client? Because you realize the server would go down and that will start like two things, TCP timeout on the client and a timeout on the cluster servers detecting, oh, it's gone. And then on the client, there would be a situation either there's a TCP timeout and it does the reconnect to the original, or he gets a witness request, please go somewhere else. And that might give a race condition on the client. Which strategy am I supposed to use?
So the question was, is there a race condition in this case where, where we have both things sort of timing out on the client side and server side simultaneously? For the witness case, it's important to remember that the client automatically tries to use separate nodes for the file server and the witness server. So in that case, if the file server goes down, we can notify via the witness channel. So we have a separate channel to basically manage the failover in that case.
Okay, thank you.
Okay.